Hello, and welcome to a new session on Cantera. Today, we will be starting a new segment that is on reaction kinetics. So far, everything that we've done in Cantera or all the scripts that we've written, they have not taken into account the reaction part. So if we can take a look at the data file, input data files, for example, I have the h2o2.yml, which is the hydrogen oxidation input data file. This is a part of Cantera database, and it is built into it. So um, if we go through this file, you see, as you've seen this before as well, the initial part of all input data files comprises of the species information. So you have the name of the species, elements that they are comprised of, and the thermodynamic coefficients, the transport parameters, and so on. However, once we scroll down, we start to see all of these reactions. So far, whatever we've done in Cantera, whatever we've learned, we have not used this part. In this segment, going forward, we will be using the reaction part of the input data files as well. Let's see how to do that. So if we have to simulate any reaction in Cantera, it is absolutely essential to use something known as a reactor. Reactors are an intrinsic part, an inbuilt part of Cantera. There are several types of reactors that we can use depending on the type of reaction that we want or the type of system that we have. So what exactly is a reactor? Let's take a quick look at that. So a reactor is, in Cantera, you could say that it is the smallest discrete unit of a chemical reaction system. So this is the smallest unit where a certain reaction can take place in Cantera. And obviously, if the reactions have to take place, they have to be reactants as well. And so every reactor will have some reactants. And these reactants are assumed to be in spatial and thermodynamic homogeneity. So which is to say that there are no spatial gradients or thermodynamic gradients in the reactants inside a reactor. So if you have a certain amount of reactants, all of them are considered to be, each part of the reactant, or each domain of the reactant is considered to be at the same thermodynamic state. And so the reactor, inside the reactor, you can conduct a reaction and which will form a product. Now that product can either be, either that product can just be taken out of the reactor and examined, or that product can be fed into a second reactor as the reactant for the second reactor, which would be, so you have reactor number 1, reactor number 2. Now you can connect these two reactors together. So the products of reactor number 1 will, once they are formed, they will now flow into reactor number 2. And you can control the flow of these products using something known as a mass flow controller between these two reactants, between these two reactors. Similarly, you also have something known as a reservoir, which again can be, so reservoir by definition is sort of an infinite source from where we can take in any species, or we can dump species there as well. And so in this particular diagram, we see that reactor number 1 takes in the reactants from reservoir, and finally reactor number 2 dumps its products into the reservoir. So we can have something known as a reservoir. In addition to that, we can also have walls. So if a reactor, so once the reactions start to take place inside a reactor, obviously the thermodynamic conditions inside start to change. So there will be a change in the temperature, pressure, etc. Now, if there is any heat that is being generated, or if it's an endothermic reaction, then the heat will be absorbed. If any of that needs to happen, then we will have to put some kind of walls on these reactors so that we can control the flow of heat. whether it is outside the reactor or coming into the reactor. But in that case, a wall will be needed as well. However, these elements are not always necessary. Walls, reservoirs, mass flow controllers, etc. There are a couple of more as well, but these are the most widely used that you will be using in most of the common scripts. But again, they are not essential. They're not supposed to be used in every script, only if there is a demand, if there is a need. And we'll see what kind of needs arise where you will have to use these elements in addition to a reactor. A reactor, however, is absolutely essential. You will always need to have a reactor in Cantera to conduct any sort of reaction. But yeah, all the other elements connecting the reactors together, reservoir, mass flow controller, etc., are not essential. They may be needed as the problem demands, but that we'll see in the future. And so finally, these are three of the most commonly used reactors in Cantera. One is the ideal gas reactor, which would be a constant volume reactor, and it is meant for ideal gas mixtures. So inside this reactor, the ideal gas law is used. Then there is the constant pressure reactor, and that's the name in Cantera as well, const pressure reactor. That is the name of the constant pressure reactor entity inside Cantera. And this reactor typically maintains the pressure of the constituents inside. It maintains the pressure at a certain value for the mixture. And to do that, to maintain pressure, obviously, if there is, say, pressure being built up, if there is reaction going on and pressure is increasing, then obviously the volume will have to change in order for the pressure to stay constant, because these are all closed systems. The reactor is a closed system. So you can have mass coming into the reactor, mass going out of the reactor, but we will have to use some kind of a mass flow controller to do that. Otherwise, it will be assumed that the reactants are already present inside the reactor. And once the reaction takes place, the products will also be present inside the reactor. They will not move out anywhere. And the last one is the ideal gas constant pressure reactor. This again has to maintain the pressure at a certain value. The only difference is that it uses the ideal gas law for the mixtures. Now, let's quickly take a look at a sample script that I have written. And this, we will not run this script. We will just look at the basic elements of the script and understand what goes on inside the reactor entity. So let's bring up Spider. All right. So this is a short script here. So what I've done is I have defined a phase called gas, and the composition, the temperature, pressure, and composition of the gas phase is this. It has hydrogen and oxygen at 1000 Kelvin. Then I have another phase called gas 2. And I've used GRI 30, GRI 3.0 input data file for this. Here I used H2O2.yml. Now for gas 2 phase, we have ethane and nitrogen at 600 Kelvin. So the first 4 lines are basically, I mean, we've seen this multiple times in the past. This is just defining the phase. Then line number 5 here, this is where we are defining the reactor. So R1 is an ideal gas reactor, which contains the gas phase. Similarly, R2 is a constant pressure reactor, which comprises of the gas 2 phase. This is the gas, R1 is for gas phase and R2 contains gas 2 phase. Now this line is very important. What this line here is doing, there's a class in Cantera called reactor net. Once we initialize a reactor, which in this case is R1 and R2, once we initialize them, we have to, so we initialize them at the initial, at t equals 0, right? Now, if the reaction has to proceed, we have to step the reactor in time. So we have to step in time to integrate the thermodynamic condition of the reactor. And any kind of time stepping or any kind of reaction progress inside a reactor will have to be done through this class called reactor net. So here we are connecting R1 reactor and R2 together using the reactor net class. And we're calling this network RNet. Now, how to step in time and what are the functionalities of reactor net, all of that, we will look at in the next lecture. But for now, what you have to understand is there will be a reactor definition needed in every kinetics script in Cantera. So this is a standard line. The reactor, however, can change. Here I have an ideal gas reactor. You can have a constant pressure reactor, ideal gas constant pressure reactor, or something else, a flow reactor as well. There are multiple reactors in Cantera. And this line also is needed. The only difference is that the number of reactors, the name of the reactors, that will change. However, this reactor net class will be needed if we want to solve the system of reactions. So that's it for this particular lecture, and we'll look at things in more detail as far as reaction kinetics are concerned in Cantera in the next lecture. Thank you.